Good morning, students. This is Anand, Assistant Professor, Department of Triple DBS. So, in the previous class, I discussed about introduction to synchronous motors and construction details of synchronous motors and production of rotational magnetic flux in the synchronous motor concept. And now, in this class, I am going to discuss working principle of synchronous motor, and at the same time, I have to discuss the behavior of synchronous motor on no load and load with and without losses concept. Okay, so first I will start with the working principle of synchronous motor. Okay, so coming to the working principle of synchronous motor, so in the previous class I also discussed about the magnetic locking concept. So same principle here we are using, but here when a three-phase supply is applied to three-phase stator winding, then a rotating magnetic flux of constant magnitude is produced. So I already said this point in the previous class also in the construction details, and at the same time for the production of rotating magnetic field concept also I discussed the same thing. So here the stator and the three-phase stator winding is connected to the three-phase supply. At the same time they produce the rotating magnetic flux of constant magnitude. Okay, so here I am assuming stator winding is bound for two poles. Okay, assuming stator winding is bound for two poles, that is N suffix S and S suffix S, and rotating in clockwise direction. So I will show the diagram. After you will understand this one. So this is the working principle diagram, principle of operation of synchronous motor. So here I am taking two poles that is N suffix and S suffix S. So here we are taking the rotor, that is consider two poles, north and south poles. Okay. So here this NS and SSN, N suffix S and S suffix S, these two are the stator poles. And if you observe this one, we have arrow marks, so directional marks, those are direction of rotating magnetic flux. Okay, next here we are giving three-phase supply to the stator. Okay, that means to the armature winding we are giving the three-phase supply. So here we have a vertical horizontal line, vertical line is there, vertical dotted line is there. So this will give the axis of stator magnetic field, the axis of stator magnetic field. So in the other diagram gives the how these poles are rotating similar to each other. Okay, so I will explain these things. Okay, firstly that's why. So with the position shown, that is this one, with the position shown in these blue diagrams, the two similar poles, that is N suffix S of stator and N of rotor. So if you observe this one, I already said that we have two poles, that is N suffix S and S suffix S for the stator. So these two are the stator poles, and we have another two poles, that is N and S. These two are the rotor poles. So from this diagram I am showing that. So with the position shown, the two similar poles, that is N suffix S of stator and N of rotor, as well as S suffix S of stator and S of rotor will repel each other. So that means this is the result that the rotor will try to rotate in anti-clockwise direction. Okay, this is the result that the rotor will try to rotate in anti-clockwise direction. So, but half a period later, so up to now we have seen the half a period, but half a period later, stator poles having rotated around by interchanging their positions. Okay, interchanging their positions. Actually, we have two positions in the diagram, that is A position and B position. So previously we have the poles, that is a stator pole and the rotor poles, both are in same direction, but half a period later, stator poles having rotated around by interchanging their positions, that is N suffix S to position B and S suffix S position A, that is point A. That means in the previous half a period, so the N suffix S at position A, point A, and S suffix S at position B, but in this half period, the stator poles having rotated around by interchanging their positions. That means N suffix S at position B and S suffix S at position B, position A, like that. Okay. So next, so under these conditions, okay, so after interchanging the positions, under these conditions, n suffix s, that is the stator pole, attracts s, that is the rotor pole that is s, and s suffix s, that is the stator pole, attracts n. Okay, that is the n means the rotor pole. So under these conditions, n suffix s attracts s and s suffix s attracts n. So hence, rotor tend to rotate in clockwise direction. Okay, hence rotor tend to rotate in clockwise direction. So previously we have in the previous half period, so we have the rotor position, the rotor tend to rotate in anti-clockwise direction. But after a half period, the rotor tend to rotate in clockwise direction. So due to rapid and continuous rotation of stator poles, the rotor is subjected to torque. Okay, so due to rapid and continuous rotation of stator poles, the rotor is subjected to torque, so which is rapidly reversing. So the torque is rapidly reversing, that is, the rotor experiences a torque first in one direction and then in the other direction. So like that it is changing, it is reversing. So the rotor cannot instantaneously respond to such quickly reversing torques. If the rotor cannot instantaneously respond to such quickly reversing torques, so with the result, the rotor remains stationary. So with the result, the rotor remains stationary. Okay. So now suppose the rotor is rotated near the synchronous speed by some means, and at the same time the DC supply is applied to rotor winding, then the stator and rotor poles attract each other. Okay. So we are assuming that the rotor is rotated near the synchronous speed by some means. So at the same time, the DC supply is applied to rotor winding. Then the stator and rotor pole, that is n suffix s and s suffix s and n and s poles are attract each other. Okay. So what will happen at the time is, so and tend to rotate continuously in clockwise direction. So there is attraction. So that's why they tend to rotate continuously in clockwise direction. It is the same speed as that of stator, that is synchronous speed. You know already the formula of synchronous speed, that is n suffix s is equal to 120 f by t. Okay, from this it is clear that a synchronous motor is not inherently self-starting. Okay, and runs either at synchronous speed or not at all. Okay. So this is the working principle of synchronous motor. Okay, and next we are moving to the next concept, that is behavior of synchronous motor on loading and no loading conditions. Okay, so behavior of synchronous motor on loading, I am taking the first case. So here, if we apply the load, okay, if we apply the load, that means the load is increased on DC motor. Okay, when the load is increased on DC motor, what will happen? Speed of the motor is decreases. You know already this point. So when the load is increased on DC motor, speed automatically decreases. So in a DC motor, armature develops an EMF which opposes the supply voltage V, called as back EMF. Okay. So in a DC motor, armature develops an EMF. Okay. So which opposes the supply voltage V is called the back EMF, that is represented with E suffix B. So the resultant voltage across the armature circuit is V minus EB, and it causes an armature current, and it is given by the expression, that is IA is equal to V minus EB by RA. Okay, IA is equal to V minus EB by RA. So and the back EMF, that is EB is equal to 5 N Z by 68. This is the back EMF in the motor, DC motor. And this is the same formula we are using in the generated EMF EG for the generators. So therefore, the back EMF in a DC motor depends on the armature speed. Okay, therefore the back EMF in a DC motor depends on the armature speed. Why? Because here the speed is directly proportional to the back EMF. That's why I am taking this point. Okay, next. So similarly, so up to now we discussed in the point of view of DC motors, and now we are coming to synchronous motor. So similarly, in a synchronous motor, a back EMF is set up in the stator by the rotor flux. which opposes the supply voltage. Okay, so what we discussed in the previous slide is applicable to this one, but here the synchronous motor, similarly in synchronous motor, a back EMF is set up in the stator by the rotor flux which opposes the supply voltage. So this back EMF depends on the excitation given to the field winding. Why? Because this field winding is connected to the rotor. Okay, that's why this back EMF depends on the excitation given to the field winding. Why? Because synchronous motor set up the back EMF in the stator by the rotor flux. That's why I am taking the back EMF depends on the excitation given to the field winding. Okay, so when the synchronous motor is loaded, okay, its speed cannot decrease as synchronous motor operates at only one speed known as synchronous speed. But in the DC motor, when the load increases on the DC motor, what will happen? The speed will decrease automatically. But in the synchronous motor, there is no change in the speed. It always rotated in the constant speed, that is the synchronous speed. There is no change in the speed after increasing or decreasing the load. Okay, that's why I am taking this point. When the synchronous motor is loaded, its speed cannot decrease as synchronous motor operates at only one speed, that is known as synchronous speed. So similar to the DC motor, armature current for a synchronous motor is voltage across armature divided by the impedance of armature circuit. Okay, so now voltage difference is the vector difference of V and EB. Okay, now voltage difference is the vector difference of V and EB, that is V bar minus EB bar. Okay, so here the armature current per phase is equal to, that is IA bar is equal to V bar minus EB bar by ZS bar. So that is, from this one I am taking synchronous impedance, that is Z suffix S is equal to RA plus JXS ohms per phase. Okay, RA plus JXS ohms per phase. So here from the formula synchronous impedance, we know that RA is equal to stator winding resistance per phase and XS is equal to synchronous reactance of stator per phase, and V is equal to supply voltage per phase, and EB is equal to back EMF per phase. Okay, this is the behavior of synchronous motor on loading. So next I am moving to the next concept, that is synchronous motor on no load. That is, it does not consist of no losses. A synchronous motor on no load, that means it is operating under the no losses condition. So what will happen at this condition means, so when the motor is running on no load, okay, when the motor is running on no load with field excitation, is assumed that no losses are present under this condition. Okay, when the motor is running on no load with field excitation, is assumed that no losses are present under this condition. That means the magnetic locking between stator and rotor is such a way that the magnetic axis of both coincide with each other. Okay, so the magnetic locking between stator and rotor is such a way that the magnetic axis of both coincide with each other, stator and rotor. Axis magnetic axis coincide each other. So at that time the back EMF EB and opposite to the supply voltage V. Okay, the back EMF EB is equal and opposite to the supply voltage V. That means from this one we are writing armature current IA bar is equal to V bar minus EB bar by ZS bar. Okay, but the difference of V and EB is 0 at this condition. That means hence IA is equal to 0. Armature current is also 0. Why? Because the difference between V minus EB is 0. That means 0 by ZS is nothing but the 0. That means armature current is also 0. Okay, at that time the motor takes no power as there is neither load nor losses. Okay, the motor takes no power as there is neither load nor losses. In practice this is impossible. So in practice this is not impossible because motor has to supply mechanical losses and iron losses along with small copper loss. This will happen in the practical. Okay, that's why I am telling that this is impossible in the practical manner. Okay, why? Because motor has to supply mechanical losses. Why? Because it is a rotating device, and iron losses along with small copper losses. Okay, so This is the magnetic locking under no loss condition diagram. Okay, at this time the phase difference is 0. That's why here the back EMF is always opposed as a supply voltage V. That means I am taking the single line, but EB and V in different directions. That means back EMF opposes the supply voltage opposes the back EMF, but the phase difference is 0. That means magnitudes are equal. That is det EB is equal to det V. So in the magnetic locking under no loss condition, that means the north pole and south pole, that is the magnitude of these matching of the two axes is in the same direction. Okay. So next, coming to the synchronous motor on no load, that means with losses. So in the previous case we discussed about synchronous motor on no load without losses, but now I am discussing synchronous motor on no load with losses. So that means when synchronous motor is running on no load with losses, okay, the magnetic locking exists between stator and rotor. Okay, the magnetic locking exists between stator and rotor. So in such a way that there exists a small angle difference between the axis of two magnetic fields. So in the previous case, there is no angle difference between the axis of two magnetic fields in the previous case. But here we have a small angle difference between the axis of two magnetic fields that will show in this diagram. This is a diagram for the magnetic locking under practical condition. That means no load but with losses I am taking. So practically it is applicable. Okay. So the previous case is not applicable for the practical. Physically it is okay, but practically that's not okay. That's why I am taking this condition. Okay. So in this one, the axis of stator magnetic field and the axis of rotor field consists of some angle. Okay, some angle. So this is the diagram to explain these things. Okay, so the rotor axis falls back with respect to the stator axis by angle alpha. Okay, the rotor axis falls back with respect to the stator axis by angle alpha like this. So here we have the axis of rotor field and axis of stator magnetic field we have, that is N sub x and S sub x. These two are the stator poles and N and S are the poles of the rotor. Okay, rotor poles. So both will have the axis with a small angle alpha. Okay, so this angle decides which amount of current required to produce the torque to supply various losses. If this angle, that is alpha, decides the amount of current required to produce the torque to supply various losses. So hence this angle is called as, we have so many names for this, is called as load angle, power angle, coupling angle or angle of retardation. So all are equal to alpha. So these all names are equal to alpha. So in this condition, the back EMF is not exactly equal to V. So it makes an angle alpha from its initial position. Okay, in this condition, the back EMF is not exactly equal to V. So it makes an angle alpha from its initial position. Okay. So this is the phasor diagram for this synchronous motor and motor with losses. So here we have, I am taking the voltage line as the reference. Okay, at this time the IA, so this the voltage V, supply voltage V lags the current IA at an angle phi, and it leads the back EMF at an angle alpha. Okay, so and the voltage, that is the supply voltage, leads the resultant EMF at an angle theta like this. We are taking the synchronous motor on no load with losses. So hence the vector difference between EB and V is not zero in this condition. So previously it is zero. Okay, hence the vector difference between EB and V is not zero, but gives rise to a resultant phasor, that is ER bar is equal to is V bar minus EB bar, that is equal to IA bar into ZS bar. Okay, V bar minus EB bar is equal to IA bar into ZS, that is equal to ER bar, that is the resultant EMF. So this resultant decides the amount of current IA. Okay, this resultant decides the amount of current IA, that is the armature current to be drawn to produce the torque, that is IA bar is equal to ER bar by ZS. Okay, from the above equation that is IA bar ZS is equal to ER bar. So from this one I am writing IA bar is equal to ER bar, that is the resultant EMF by synchronous impedance. So under no load condition, alpha is very small and hence ER bar is also very small. So current drawn by the motor is also very small on no load condition. Okay. Next, coming to the second case, that is the synchronous motor on load. So previously we discussed about the synchronous motor off load, that means no load conditions, and now we are going to the synchronous motor on load condition. Okay, so in this one, as load of the synchronous motor increases, load angle. So if you increase the load of the synchronous motor, there is no change in the speed, but the only change in the load angle, that is alpha. Why? Because the angle by which rotor axis falls back with respect to stator axis increases, but there is no change in its speed. So I will set this point. Okay, the angle by which rotor axis, that is alpha, falls back with respect to stator axis increases, but there is no change in its speed. So as alpha increases, the resultant voltage, that is ER, increases, and current drawn by the motor also increases. Okay, so this current produces the necessary torque which satisfies the increased load demand on the synchronous motor. Okay, this current produces the necessary torque which satisfies the increased load demand. Next, the magnetic locking still exists between the stator and rotor. So the angle alpha goes on increasing as load increases. The maximum permissible limit of alpha is 90 electrical degrees. Okay, so it is increases by 90 degrees. Magnetic locking between stator and rotor breaks. So up to alpha is equal to 90, we have a magnetic locking between stator and rotor. So when the alpha increases by 90 degrees, so the magnetic locking between stator and rotor breaks, and motor comes out of synchronism and stops. Okay, and motor comes out of synchronism and stops. Okay. So that means this is the diagram we are considering for the magnetic locking under load condition. So here the alpha is by 90 degrees. At that time the synchronous motor comes out of the synchronism and stops working. So this is the diagram to explain this magnetic locking under load condition, and this is the phasor diagram we are taking. So here we have the losses, that is IIs. Okay, that is the synchronous impedance drop. And here I am taking the voltage as a reference phasor. Okay, and here the IA lags V by angle phi, and it leads the back EMF at an angle alpha, and it leads the ER, that is with an angle theta. And here we have the drop, that is IIs. So here ER is equal to resultant EMF is equal to IIs. Okay, so the torque produced at alpha is equal to 90 degrees is the maximum torque, that is called pull out torque. So actually the torque equation I will discuss in the next classes, in the coming classes. So just now in this class I am going to discuss just pull out torque. So this is one of the type of the torque in a synchronous motor. So when it produces this, so when the alpha is equal to 90 degrees, it produces a torque that is the maximum torque, that is called pull out torque. Okay, so the relation between torque produced and load angle alpha is shown in this diagram. So here the characteristics is drawn between maximum torque, that is pull out torque, versus load angle alpha. So when we get the pull out torque, when alpha is equal to 90 degrees. So if you observe this diagram, so here the curve is drawn up to the maximum torque. So the maximum torque occurs when alpha is equal to 90 degrees. So that is called pull out torque. That is the maximum torque, and that one is called pull out torque. Okay. And we have decrease in the torque, that is after maximum torque occurs, and after it will decrease slightly to the normal load angle, that is 0. Okay, like that it will happen. So next, so coming to the next concept, that is analysis of phasor diagram for the previous concept, that is previously we discussed about these things. So here I am taking the voltage phasor as a reference, and here in this one the voltage lags Ia at an angle phi and leads back EMF at an angle alpha and leads resultant EMF at an angle theta. Then it consists of the ER is equal to Ia, that is at the angle alpha. So that is, so let alpha be the load angle. You already know this one. So let alpha be the load angle corresponding to the load on the motor. So at that time the armature current per phase is Ia is equal to ER by ZS. ER by ZS, that is the armature current per phase, and resultant EMF ER is equal to root of V square plus EB square minus 2 into V into EB into cos alpha. From this one, synchronous impedance ZS is equal to RA plus JXS. So from this one we have to take the formula, that is theta is equal to tan inverse of XS by RA. Okay. So here I am taking the phasor diagram, that is this one. So here by using this right angle triangle rules, that is theta is equal to tan inverse of XS by RA. Here the angle theta is called as internal machine angle or impedance angle. So theta is called internal machine angle or impedance angle. Alpha is called load angle or power angle or coupling angle or angle of retardation. So it is constant for a motor. This theta is constant for a motor. There is a synchronous motor. Okay. So the significance of theta tells us that, okay, the significance of theta, actually this theta is constant for the motor. So the significance of theta tells us that Ia lags behind ER by an angle theta. So practically RA is very small compared to XS, and hence theta tends to 90 degrees, and phi is equal to power factor angle or angle between V and I. So in the phasor diagram, so the angle between V and Ia is the phi. Okay, this is the power factor angle or angle between V and Ia, and cos phi is the power factor at which motor is working. Okay, and the nature of this power factor is lagging. In this condition, the power factor is lagging. So I already said that in this phasor diagram. So the voltage lags Ia at an angle phi. That's why it is a lagging power factor. So the nature of this power factor is lagging. If VA lags Ia by an angle phi, why it is leading? If IL leads V by an angle phi. Okay. So that is the condition I am taking. Okay. So thank you for watching this video. In the next class, I am going to discuss the different talks and phasor diagrams of synchronous motor, and next I am going to discuss power equations of a synchronous motor like that. Okay, thank you for watching this video.